Perfect. So yeah, thank you very much for having us. We're really glad to share some insights of how we do run data science projects at N26. So there might be a little bit less technical details presented today, but kind of more also like the organizational challenges or skills that might be different from purely working in an academic field or solving like a Kaggle competition, but how kind of which skill set is an additional needed to make data science projects successful in an organizational business context mostly. Yeah, so that's what we're going to talk about today. But maybe quickly first, who are we and where do we come from? So N26, this is where we work, is kind of, if you haven't heard about it, is this kind of a mobile bank that has launched 2015 ago. By this time now, we originally launched the bank in Germany, have expanded then to all European currency countries, and now also to the US. We have more than 5 million customers, which gives us quite some data to play around with now. So we are mostly design and usability focused. It's kind of our main competitive advantage. And to talk about the two speakers today, I'd like to introduce my colleague Giorgio, who is a senior data scientist at N26. He has a very strong background in statistics and has worked a couple of years in the consulting area in Italy for data science projects and implementations, and mainly in the banking industry. So has quite a diverse and strong background in that. He now works for N26 since 5 months, which in a startup is much longer than one might think at the beginning. And outside of work, he climbs and enjoys playing punk rock.
So I'm happy to introduce my colleague Philippe Billaudelle. He is a senior data scientist at N26. As opposed to my 5 months in the job, he's been here 5 years, which is quite a long time. And actually, the legend is that he was the 7th employee of the company. So he has a background in business and law, and he's like a self-taught data scientist, which means in data science, it's a broad field, and there's room for like smart people, even without a super strong technical background, and he's like here to prove it. And he's also acted as head of data science for over a year. So you can really see how he can make an impact in data science through his like journey at N26. And when he's not like cross-validating models, he would train for trail running competitions.
Thank you, Giorgio.
Moving forward with what we're going to cover today, just to give you a quick heads up, we will spend a few words on what do we do and how we do it. And then we will move to what represents for us the phases of our data science project. So how do we understand the business problem? We prototype a predictive model, and then we serve this predictive model into our production system.
Thank you, Giorgio. So yeah, I'm going to start by talking quickly about what do we do in general, like in our everyday work, what is our main focus. And I'm kind of focusing what this work consists in, like the fintech environment. So as a like also tech product driven company, and how that might be different, as I said, from the academia world, or maybe also just from studying it. And then I'll also be quickly talking about like the difference in positions. So we do also have data analysts and ML engineers, and see how that is different, or how the skills might be overlapping, but the work itself is a little bit different. So coming to the first point. So if I have to describe of how data science at N26 might be a little bit different from also like especially big companies that have larger data science teams, is that we define ourselves as being full stack data scientists, aka we kind of work on a data science project from beginning to the end. So that means actually we go gather data, try to understand the business problem by interacting with stakeholders, and have to do all the cleaning up of the data and prototyping it. And once we have prototyped it, and we're not handing it over to a different team that would implement it actually, but we keep the responsibility for actually productionizing the model and serving it into like our production systems. So that's kind of the entire journey that we are fully responsible for end to end. And how is that maybe different from a data analyst? And certainly some skills are overlapping, but in our world, at least data analysts are more focused on providing descriptive statistics and like for reporting purposes for the management that then kind of can make better decisions based on data. On our side, the data scientists, we are really focusing on delivering data-based and user-facing product features. And by that nature of the work of delivering like user features and real product features, we have to be also very good programmers in order to write like stable applications that can actually then implement these user features. So I would say the programming nature of our work is what differentiates us maybe from data analysts. So what's the difference then to an ML engineer? So here the border is a little bit more blurred, I would say. And for a fact, N26 did not have ML engineers for the first 4 years of operation. So we only started by the end of last year to kind of hire a team for ML engineers. And then the reason is because as systems get more complex, as we have more users, the technical challenges become much more complex, and the non-functional requirements like security and stability become more difficult. And that's what sometimes you probably would need a specialized skill set, and someone like me or other people from a maybe more statistics background might not have all that computer science knowledge that is needed to really solve more complex problems with real-time data applications with big data. And that's kind of where we see ML engineers coming in. And we kind of decided that these engineers will advise and support data scientists and provide them tools to productionize their own systems, but not really taking over the entire model. That brings us to my next point. And how do we actually how do we fulfill our responsibilities that I've outlined, and how do we spend our daily activities? And I think we can cluster our activities into 4 main phases of a project. And the first phase is understanding the business problem. And I think that's the first order of business. If we want to really deliver positive impact and create value for the company, we kind of need to talk to stakeholders and understand the problem they are trying to solve before we even start with any more data science work, more in the classical term of like feature selection, algorithm selection, and model evaluation. So only when we kind of have really determined the problem statement and the why of our work, we kind of start the more classical work of a predictive model. That can take sometimes even weeks before the full problem is defined. Then we do like the classical work of feature selection, algorithm selection. And then always the model evaluation happens in the business context. Can we answer the original business problem that we kind of worked out together with the product managers and the stakeholders? And as I said, maybe something which is different in our context is that we as data scientists are also responsible for then actually serving the model, aka meaning we have to write production ready code, integrate it into production systems, writing tests, etc., etc. And I think Alessandro mentioned that in the talk before, and I think that's crucial to repeat. Communication is so important in kind of the business context. We really have to iterate, even in like a tech-driven startup as N26, come back again and repeat how important data science is and what it can deliver, to kind of remove a little bit of that mystery, what it can deliver and how it works, because that will make data science create more impact and we get kind of prioritized in more projects. To give you a brief overview how we use data science in N26, I would say there are 4 main areas of machine learning applications. Like one is financial crime prevention, so detecting whether users are fraudulent, behave fraudulent. Second one is credit risk management, similar to the use case that Alessandro presented just now. I won't go into details here. Something more advanced or different and innovative, let's say, is called what we call transaction categorization and smart statistics. This is where we try to categorize all types of spending and incomes of users and provide them with kind of overviews. We even are going into the domain of forecasting what the expenses and revenues might be in order to provide them like some clever insights on where they might have like financial problems or inequality, or just providing them kind of with the overview. And last but not least, we also have a very successful chatbot running that kind of automates already 30% of user inquiries, and kind of we just need less humans to answer these. So today talk, we're gonna focus more on these first two examples and kind of what challenge they have brought us in the past. So just before we go into the structure that follows quickly, how do we do credit risk management? Like one of the most important applications, we predict the credit risk default, so the probability a user will not pay back their loan or will pay back their loan over the next 12 months. For that, we are using it's a binary classification problem, and we chose to do that in a Bayesian logistic regression. And for the reasons, I'll come to that later. And we mainly do that based on features from financial account history. We do evaluate the model on the RC AUC score, and our productionizing consists of daily retraining and batch predictions, as well as serving our model on a REST API. And the second part that we also use an example throughout today's talk is the financial crime prevention, where we try to detect fraudulent users. Again, this is a binary classification problem. This time we opted for isolation forest and an unsupervised model for the reasons of that we're also going to talk about. And here we're going to use a much bigger variety of features, which will include account, transaction, and behavioral data. So the first deep dive of today will be about, and I really want to emphasize this, about how important it is to actually understand the business problems. And I'll talk about this kind of what are the typical problems that we are getting. So this is a very concrete example of a request that I would got, or that I got in the past, as the product manager comes up and asks, hey, can we not just predict a smart user risk score? So this is a typical example of a very like broad and undefined and unclear objective. So it doesn't really provide the context or any hint to what a success criteria is, or what the target variable is that we kind of need to optimize for. So that's really hard to work with. So at that point, it is really about communication, going to this to the product manager and asking. So I like to really focus on the problem and not like the proposed solution, like can you produce a risk score, but really asking why do you need this? What is the actual problem that you're facing? Because that will provide me much more context and open up a much wider space for problem or like for solution finding. And yeah, that's kind of, it's really essential to drill down what the context is, why we're solving it. And that will also give you the hint of which data we could use and if any data science solution is even useful and applicable. So many times also we got problems that even don't have so much, where ML probably wouldn't have so much an impact. So again, I want to emphasize talking to many stakeholders also that will be impacted by the solutions that you're trying to build will really help you get the context, like give you insights on which data you might be able to use to solve that problem. So what does like a good problem statement look like? This is basically what we worked out after a lot of conversations. Is actually what we want to have as a problem statement is, can we accurately predict the probability that the German users will default the next 12 months on their overdraft, even if we don't know their credit bureau history. So of course, that's a problem statement that we probably want to achieve. We didn't answer like all the questions we have, and that's not the goal here, but we really have detailed the questions to an extent where we can actually start work in a data exploration out. Like we can now define in a statistical term, what does accurate mean? What are the success criteria in a statistics in a statistic term? What is the definition of a default? Like there's so many different ways you could probably define a default. Is it after the first 30 days they repaid or 60 days? And then the main problem that we had in N26 is we didn't know a lot of credit bureau history of users because they were either even too young or expats moving recently to Germany and didn't have much of a history. So that actually really gives a context and also guides the problem solving. But once you have your problem statement, you also want to think about non-functional requirements a lot and how that might impact your model decisions. So one good example for us is that N26 operates in a highly regulated environment. So just two examples of that is the GDPR, general data protection regulation in Europe, as well as our general compliance department that makes sure we are in bounds of all laws. And what is the impact on our modeling? And as Alessandro mentioned that earlier, so I'm really jumping on the train here, is explainabilities of models is one big part, because you would be faced with like traditional risk management people from a bank that don't have that technical or statistical education, and also the regulator mostly even more, and they kind of want to understand how the model works, how the mechanics of it is, because they will need to approve it and see how it works. And kind of to cover that explainability aspect, we found that it's much more easier to work with more traditional models like logistic regression, and even so the Bayesian modeling, because it provides like rich visualizations that you can go through with these stakeholders and explain them what the model does, which features are important. Of course, as Alessandro mentioned, you have like Shapley values, feature importance, algorithms that can be handy, and it's something that we are also using, and sometimes we just want to opt for the more simple version. Yeah, that's basically what we have to consider in non-functional requirements. So maybe just to recap, what is important when kind of trying to understand the business problem? What are the questions that we're trying to answer? So first, again, to iterate, why and what problem do we really want to solve? That also leads us to a question, talking to people, which data do we actually have available? Because that, of course, will lead our feature engineering approach, that will lead our, how can we define the target variable? Do we have to maybe gather additional training and labels by employing humans or other ways? And then most importantly, it's really critical to agree on a business metric with your stakeholders and a product manager that is really measurable and that you can tie to a statistical measure that you're optimizing for. And then last but not least, in a highly regulated environment, you always want to consider potential legal and regulatory restrictions, be it fairness, as Alessandro mentioned, but also explainability, the 2 points. And there are, of course, innovative ways to solve that, or sometimes you want to just simplify things. And now I'm handing over to Giorgio.
Thank you, Philip. I hope everyone can hear me. All right, so I got the funniest part of the presentation, and I will be sharing with you how do we prototype a predictive model in N26? What do we consider are the most important steps to be taken, and some of the challenges that we face when prototyping a predictive model? Because, of course, the first thing you should do after you have this reached clarity on the business problem is to build a prototype. You cannot just go in production with some random idea. Therefore, the first most important step of prototyping a predictive model would surely be that data gathering and transformation. And if you are familiar with Kaggle competitions, or if you run small data science projects, it could happen that you have your data in a nice CSV file and you just start working on your model. That's not the case in a real life project, at least at N26. What you usually have to do is to locate and merge multiple data sources. And in order to do that, you need once again to talk a lot with domain experts, with data warehouse experts, data analysts, and people in charge of the process to collect such data. So to give you an example, when collecting data to build a user risk score that would score the users as soon as they open their account, we first need to understand what data there is available when a user opens their account, what is tracked, where it is, who owns those tables. That's a very important process and should be done carefully, because the model will be only as good as the input data at the end of the day. Once you have good input data, you move forward to another interesting part, feature engineering. It's where your contribution as a human and as a data scientist could be really valuable, because it's where you model concepts from domain knowledge into features, into variables that the model will be able to understand. Again, it's crucial that you communicate, that you talk with people who have this strong domain knowledge, who deal day-to-day on an operation basis with the problem you are trying to solve with machine learning, to understand what are the patterns that they see, what are the behaviors that they see, and then it will be up to you to model them into variables for your model. Interesting fact, in N26, to optimize for computing performance, our user risk score model does its feature engineering embedded in the SQL queries from the data warehouse. So once you have your feature set, you are in a great shape and you can move to model training and evaluation. Once again, talk with the expert, but not this time, to be honest, because the expert is you. We, data scientists, we are experts about model training. We know what we should do. We know how to do it. So that's great. The danger here is that we would invest a lot of time in modeling activities, which impact is not sure, or it's unclear, or even worse, is not relevant. Therefore, my advice would be always keep an eye on the end goal of your modeling activity and don't overdo it. When your model is good enough, it could always be better, but when it's good enough, stop it and convey your energy towards building a great presentation. So moving to presentation, that's like, I think, the most important part of prototyping a predictive model. Your results are really worthless if you're not able to communicate them. Presentations should be very easy to understand, short if possible, and focused on the solution rather than the methodology. So what was the problem that you addressed and how does this solution solve it? If you are able to present your results in such a way, then you are a winner in data science. So this is about the process of prototyping a predictive model. What I'd like to share with you now is some of the challenges that we face as data scientists. And one of them is what is called selection bias. So it's quite an interesting concept and quite tricky as well. And in fact, sometimes we asked about it during job interviews too. So what does it have to do with Top Gun? Not much. It's more something to do with the sample that we're looking at and how well it represents the population it's taken for. So during World War II, the Royal Air Force was doing statistical analysis on the planes coming back from battles. And at the beginning, they were patching the planes on those parts which had a lot of bullet holes because they believed these planes were hit there. So that's where we should reinforce them. That was wrong. And the statistician, a guy called Abraham, figured it out. And he figured out that they were doing some kind of selection bias, and more specifically, survivorship bias. They were not looking at all the planes that were hit and that fell during the battle. Those planes were hit in parts that, of course, they couldn't detect. So they figured out that planes should be patched and reinforced wherever they didn't have any bullet holes, because if they were hit there, they would have fallen during the battle. So this is quite a powerful example about what is the importance of selection bias. Now, in World War II, it was a matter of life and death for planes, for warplanes. Luckily, it's not like that in N26, but still it's something very important that we take care of. So moving to the next slide. Philip. Here we go. About selection bias, when dealing with user risk scoring, we actually see two issues. The first one is that we're dealing with an imbalanced data set. What does it mean? That luckily, most of our customers are not fraudsters. Therefore, we should be aware that when we draw a sample from the population of our customers, just a handful of them will be fraudsters, not the majority and not even half of them. This is like a concept a data scientist should be pretty familiar with, but it's really so impactful when training a model and when explaining what's going on in the model to people outside from data science that I want to spend 15 more seconds discussing this with you. How do we address the imbalanced data set? First, it should be addressed within your model. So what do is we feed to the model the ratio of the negative to the positive class as a learning parameter. And second, you should really measure your model with an appropriate performance metric. In our case, we use the area under the receiving operator curve. But why is this important? Imagine that only 2% of the customers are fraudsters. Therefore, you could be the model that says every time without any statistic behind that a customer is a legitimate customer. And this model would be right 98% of the time. So you can see how a mistake on this would have a terrible impact on your model and on your business. Something else about selection bias that we should be aware of is feedback loop pitfall. So imagine that our user risk score model scores our customers, and then those customers are identified as fraudsters, labeled as such, and then we retrain our model again on labeled identified fraudsters. We would be in danger that our model learns to identify new fraudsters based on the old fraudsters that it was able to identify. And this would be a very bad situation because the model would be basically learning from the past version of itself. And if you want to see it from the other way around, the fraudsters that were not identified in the first place by the model would never be identified again. And what's worse, the model would actually learn how not to identify them. So this is something tricky. We should be aware of it and we should address it. How do we do it? First, we use an unsupervised approach, namely an isolation forest. So it means that we are looking for outliers, for observations that have a feature set very unlikely in the other observations. We don't use a supervised approach. We don't train our model to understand the label. And the second point, it's not in the model, it's in the context. The customers are not reviewed only based on the output of the user risk score model, but also based on the output of different multiple independent systems. So for instance, a customer would be also reviewed if a transaction monitoring tool would flag up a suspicious transaction about that customer. Coming instead to credit risk scoring, we also faced some selection bias issue while building this model. So at the beginning of the history of our credit risk scoring engine, we had to build a model for the population on the bottom of this slide, the typical customer for N26, young, freelancer, expat, student, people that would not have granted credit in the past and that had a very poor credit history. But the only available data that we had, it was for people more like in the top of this slide. So people in their 40s with a stable financial situation, a stable job, and that probably already had credit granted in the past. So you can see there's a strong bias in building a model with data from the top for a population on the bottom. What can we do about it? Actually, nothing. We can be aware of it and we can find out a way to make it work. So that's what we did. The first step towards it, it's awareness. So be aware of what's going on in the model. Are you building a biased model? That's fine, as long as you know that you are doing it and you know how and where the bias is distributed. And in order to get this knowledge, you should do a lot of data exploration. Second, we run experiments. Grant, to begin with, small credit based on the output of the biased model. It's probably not the best, but it allows us to start building an unbiased data set, so credit history for the population that we are interested in. And don't forget to grant credit to bad users too. If we only granted credit to users with a very high credit risk score, then we would never know anything about the false positive rate. We would never know when the model is performing bad. Last but not least, do a frequent model recalibration. The sample we are trying to learn for is small, it's quickly changing, and the model is biased. Therefore, recalibrate it as frequently as possible will only help to make it better. So that's it about prototyping a predictive model. I think we can move to serving a predictive model. And I think it's Philip's time again.
Yep. So yeah, exactly. Once we prototype the models and faced and solved the problems that some of the problems that Giorgio mentioned in kind of about the real population that we kind of modeling for, then it's about time checking back with the stakeholders. And once you decided like the MVP and the use case is kind of being addressed, then you want to serve your model, and that's kind of the topic now. And I would say the first quote that I I encountered when moving to the data science and working with programmers was premature optimization is the root of all evil. So every programmer basically, but originally attributed to a person called Donald Knuth. What does it mean for me, or what's the idea behind it is that even though you want to think about how your software and your solution might scale to the millions of customers, in kind of about the scalability and for bigger applications, you probably don't want to implement that in your MVP, in your first solution that you're building. So even if you confirm the use case and your prototype, it's still something else to confirm it then in the real use case. And when you deployed it, you want to first test that it actually works and generates the value for the company, for the user, before they then start making the model more complicated and develop it. So I think the order of business from that is don't overcomplicate things, and first order of business, make it work and test your use case. Basically, if I had to reformulate this in a simpler way, simplify everything you can in your first iteration. So you want definitely to think about how your service might evolve. You want to write readable, efficient code that you can build upon. You don't want to invest into technical debt, is my learning, but you want to make it as simple as possible. So what could that mean? What does it mean to keep simple, especially data science applications? I think the biggest learning for me was, do you really need real-time data for your predictions? Or are the performance gains on like the most latest transaction information about the user rather marginal for the predictive value, and does not even justify the added complexity for the heavy data pre-processing in real time, for the heavy feature calculations and storage of these features? So kind of usually, and in many applications for credit risk, for example, we often fall back to not include all the transaction history from the last days or even the last minutes, as it might be, but rather use completed full weeks of data, or even months in some use cases, which you only need to calculate features and store features for full completed months per user, and don't have that heavy recalculations. And that makes a tremendous difference in many ways in your system's architecture, in the data retrieval performance, etc. So really be aware of that. Sometimes you want to sacrifice probably some performance gains and in your model by making it simpler and making predictions on fully completed older data. And the second thing is, do you then, and that usually comes along with real-time data, is do you need to calculate your predictions on demand? Like, do you need to expose APIs that kind of have high availability SLAs to the other services that you're exposing it to? Do you even want to integrate into like a streaming application and an architecture like Kinesis, Kafka streams that you might not be used to and maybe prone to error from your side? And especially if one of these like real-time on-demand calculation fails, you kind of need a system of on-calls that would quickly go and fix about your data science services that have failed. So, or can you maybe go on, if you're not calculating things on demand or not relying on real-time prediction data, can you maybe implement a more simpler batch process that would update your predictions from time to time and write them to a DB? Yeah, and then the other thing is, of course, how many features are you using? How long is your look back period for calculating those features? And that all that influences how much data you need, how heavy the pre-processing and the data calculation will be, and how much time you have to invest into like optimization of your data retrieval. So from my experience, especially for the first iteration, is simplify it if you can.
Thank you, Philip. And now I will be sharing with you one last example about something that challenges us as data scientists when we put our models in productions. Our models are there, are having a great time, but something could go wrong. And so let's discuss model drift. You see in this image, there's a computer. I don't know if you recognize it. I hope so. That's the Macintosh, the first like computer produced by Apple. It's a fantastic machine. It was a game changer back in the days, but nowadays, if it wouldn't be any good to any of us. Does it make it a bad computer? No, but actually the world around it changed and now it's not useful anymore. Could this happen to machine learning models? The answer, of course, is yes. And going forward, there's something called model drift, which happens whenever the model you are working with, the model that is in production, is no longer a trustworthy representation of the reality it's trying to capture. And let's see it in practice. There's something about context awareness. What happens when 2 or 3 months ago you read this in the news? N26 exit UK market following Brexit. That's quite a powerful piece of news. It was all over the news a couple of months ago. And it has an impact also on the work of a data scientist. For instance, in the case of user risk scoring, we had to remove UK customers from training population of our models. That's because fraud patterns are very country specific, and we don't want our models to learn how fraudsters behave in the UK when we don't serve UK customers. So it's something very simple, but at the same time, extremely impactful. One more thing that you should try to do with your models in production is called continuous performance monitoring. So what happens if your test set performance is this hamburger from the commercial and your real life performance, it's just a bit disappointing? You don't want to be in that situation. You want to be in a situation where you know that the performance measured on your test set when you trained your model, it's comparable with the performance that your model has in its day-to-day activity. Or it's not, but you want to know what's going on, to be aware of it. It might seem it's easy to implement some pipeline to continuously monitor the performance of your model, but it's not actually. Some challenges that we face during that process. Well, are you saving the predictions of your model? And that might seem like a trivial question, but if your model deals with transaction data in real time, it means that you would be saving a huge number of predictions with a huge impact on size of data that you would be saving. Again, is there any lag between when the score of your model is calculated and when whatever entity was scored then gets manually reviewed and labeled? In the case of user risk scoring, there is. It takes roughly 30 to 45 days on average for a user to be reviewed after the model scored that person. And if you think about it, I might be scored today, but I might commit some fraud in 1 month from now. So that just makes sense. And you should really be aware of what is the process from an operational point of view after your model in order to then build a proper pipeline for continuous performance monitoring. And I think this concludes our today's talk. I hope you enjoyed it. I hope it had something valuable for you. We can maybe quickly recap what we discussed. So we had a short introduction about what do we do and how do we operate. And then we described our phases for our data science project. That would be understand the business problem, prototype a predictive model, and then serve this predictive model. What we try to convey here as closing messages is 3 simple points. Knowledge is power. So be aware of whatever is going on. Be aware of the context your model operates in. Be aware of the performance that your model has in its real life. Be aware of where your data is coming from. Be aware basically of everything. If you have this general awareness, then you will be able to take the right decisions also when dealing with modeling activities. Be focused on the impact. Look out for the impact of your data science work. Data science can have can be of great help to organizations, but as data scientists, we should always think how our models will impact the final users and how they will impact the business KPIs. Otherwise, our work will not have the shine it deserves. And in the end, simplify. Every time you can, simplify your application, your architecture, your model, and the way you communicate. In this way, you will be very well understood by everyone in the company, and hopefully you will be a successful data scientist. So thank you very much for your time, and thank you Alessandro for the speech before us, and thank you Machine Learning Milan for inviting us. We are happy to take your questions now.